almost the full group of recipients of my email, maybe except for one or two who have other obligations. I think we can start. I'm happy that we have another talk that has been offered for our research seminar by Klaus Probis from the University of Vaasa in Finland, where it's only 5 degrees by now. He is waiting for the first snowfall. We are actually thinking about whether we should apply for the Scandinavian visitors professorship that we have in Kiel for him for next year. So if we do and if we are successful, then you have more chance of interacting with him. Yeah, I'm happy that we have you on board once more.
Yeah, thank you so much. Thank you so much.
I simply hand over to you.
Yeah, thank you so much. Welcome also from my side. It's a big honor to me that I can present one more time at the seminar, and thank you so much to Professor Lux for organizing this online seminar. The study that I would like to present today is entitled "When Storytelling Gets Published in Scientific Journals on the Momentum Illusion." So, first of all, the first impression that you might get is this a provoking title? And the answer is probably yes. But on the other hand, obviously, if you somewhat slightly provoke in your title, then it also generates some attention. And my former supervisor told me that both is good, positive and negative attention from the media. So, and one interesting thing is that I don't know if who of you is familiar with the book The Black Swan. So this after uploading the study on ResearchGate, there were in a couple of days hundreds of downloads and full text reads, and one of the scholars who was interested in the study was Nero Tulip, who was associated with NY Stern University in New York, Department of Engineering. And the interesting thing is that if you read the book The Black Swan, you might have a good guess that Nero Tulip is Nassim Taleb, so the author from The Black Swan and other books that deal with extreme events. And actually I was also briefly in contact via ResearchGate, and of course he is a little bit undercover there, but anyways, it's interesting to see that even this top-notch scholars, I would say, are interested in this kind of studies. So that was just a funny, somewhat interesting opening of this presentation. So what's the motivation here for this study? The original paper on momentum, first published in 1993 from Jigeresh and Titman. This study was cited more than 14,000 times, which suggests that there's a huge body of research going on. Then there's a recent literature review from Beast. I think this is actually a German guy, or Austrian probably, who summarizes the results of 47 out of 60 momentum studies that have been published in what scholars might refer to as top 3 journals in finance, the JF, the JFE, and the RFS. The leading finance journals, at least according to some lobby. Then Colley, Moskowitz, and Pruitt, and they have documented, this actually also a JFE paper, they have documented that scholars have come up with many different explanations which are termed in that study here as stories for rationalizing the existence of the momentum premium. And in their paper, I'm citing here, they argue, despite its widespread influence on the finance profession, momentum remains a mysterious phenomenon. So the common foundation for all of these momentum stories is that the momentum anomaly or the momentum investment strategy generates on average a return of 1% per month, with the t-statistic indicating significance on any level. And this has been confirmed in numerous studies, including replication studies. In the paper entitled Momentum Crashes, published in the JFE from Daniel and Moskowitz, 2016 paper, they document that strong positive average returns and Sharpe ratios of momentum strategies are punctuated with occasional crashes, manifested in huge negative returns that can be pronounced and persistent. For instance, here, what you see here is I'm investigating 700 months of the strategy implemented in US stocks, and here I show in this table here the 7 months that have the highest volatility, and 6 out of 7 are negative. We see also perhaps 2009 in the wake of the financial crisis, when the market rebound, then we saw this one of the worst momentum crashes, one of the worst negative returns, which occurred in March and April, and 2 consecutive months after each other. First, in March 2009, a negative return of minus 39.6%, and then in April again, minus 45.21 negative return. So in only 2 months, a huge amount, or the vast majority of your wealth, would have been wiped out in an instant. So that is the CRM, is the compounded return for momentum, and here you see the timeline. It's from December 1964 until December 1989, which is the original time length or data sample of the paper, or data sample used in the original study from Jigadesh and Tintman. And you see an almost exponentially increasing trend here in the compounded returns. And of course, it may be not surprising that scholars and also the finance industry became interested in this investment vehicle. What you see here on the next slide, I show the lower line here, the lower graph, shows the evolution of the original strategy for the expanded sample. So here's the sample. It covers the original time period from 64 to 89 and until this year. But the gray graph here shows the evolution after excluding 1% of the distribution, and that is, I exclude those months that have the highest volatility, which I just showed in the previous table. And you see, these are obviously 2 very different animals. Okay, so you see that 1% of the observations, those extreme observations, 1% of the sample, they make out more than 90% of the compounded momentum return. So the purpose of the study is therefore to examine the risk of the well-known traditional stock price momentum strategy implemented among US stocks. And we note that the standard momentum strategy is based on a 1-year prior performance and holding period of 1 month. And this has been also proposed as risk factor in the Farmer and French study from 2018 in the JFE. So they proposed the 6-factor model, and what they do is basically they add to the 5-factor model the momentum factor. So, and for those of you who are not familiar with the momentum strategy, so what are you doing is, okay, you have, let's say, time window of 1 year. Then you, for all stocks in your stock universe, you cumulate the returns from T minus 12 until T minus 2. Then you buy those stocks that have the highest past returns in this time window, and you short sell those stocks that have the lowest cumulative return in that time period. So you keep that 1 month ahead, then you rebalance the portfolio again. You skip the most recent months. Why are you doing that? Because of the short-term reversal effect. Because the short-term reversal effect tells you that it suggests sort of negative autocorrelation. So those stocks that have performed very poorly in the most recent months, last month, they tend to outperform those stocks that have performed very well. So you want to exclude this effect, since it might pollute your momentum strategy. That's why you basically skip in the setup the most recent past months. So, but that's basically this standard strategy that has been discussed in the vast majority of momentum studies. So in the corresponding finance literature, risk is typically measured in terms of its variances or volatility, which is just the square root out of that metric. Data and methods of the study, how is proceeded here. So daily returns are used for the momentum portfolio, which is a self-financing investment strategy, and then realized variances are computed for different time frequencies, respectively resolutions. So we have a high frequency, so we have a high resolution and low resolution. So 5 days of summed up daily squared returns is sort of proxies the weekly realized variances, whereas the sum of 125 squared daily returns is the resolution for semi-annual realized momentum variance. So then log regressions are used to estimate the power law exponent for these various resolutions, and this is I would say, traditional strategy. There are obviously a huge amount of different strategies how to get the power law, how to estimate the power law exponent. That is probably the traditional approach, which is also used in Mandelbrot's study, and he argues in his last book that log regressions, if the slope at different frequencies is about the same, that is prima facie evidence for a power law behavior of that data set. Then statistical tests are run for testing the invariance of realized momentum variances across resolutions. Then sample split tests are run to explore whether the estimated power law exponents are stable across time. So the invariance, that's what power laws is all about. The invariance is tested across frequencies and across time. Then the plausibility of the power law hypothesis is tested by explicitly testing the log normal distribution against power laws. So that's probably needs to be done, since there is obviously a literature that documents that realized variance is close to log normal distribution. And here we investigate, is that really true? Does it really make sense for that data set? Then a more data-driven approach as a sort of robustness check is implemented to re-estimate the power law exponents, and it is tested whether those estimates are covered from the confidence interval from the point estimates derived from log regression. So we basically want to figure out, okay, are those give those different procedures statistically the same estimate? So that's basically what you are interested in here. And then the effect of time aggregation is tested, which is obviously an important issue in the context of financial risk, since there's obviously a literature arguing that as you expand or as you aggregate time at lower time frequency, everything is normally distributed. So actually, I can recall that during my doctoral studies I learned that as well. So the academic teacher, he actually argued that stock returns, if you take quarterly data, they are usually close to normal distributed. So that's what we are also interested in here. Let's go directly to the results. That's probably most interesting here, since log regressions, I suppose that's sort of common practice. So here we see for the resolution using 5 squared daily returns, the corresponding plot in the upper part, and in the lower part I show you a simulated time series, 10,000 drawings from power law with exponent of 2.1. So just in order to contrast simulated data and real life data. If we now move on to here we use a lower resolution. We include now 20 squared daily returns in the realized variance measure. Here we have 60 days, 90 days, and 125 days. So we see the resolution is lower as we include more sample observations in our measure of the realized variance. But we see these peaks, they look still very similar. Yeah, so it's just a different resolution of the data. Here we see the log-log plot and the regression line. The R squared is between 96 and 99, so it's a very well fitted data. Here we see the log-log plot for the resolution of 5 days. Here we see it for 20 days, 60 days, 90 days, 125 days. So they look very, so visual, if you just use visual inspection, you see that the slopes, they are very similar. But now we want to have a real analysis here. So here are the results from performing log-log regressions. We see here in the fourth row the estimated alpha, the estimated power law exponent. We see point estimate for, say, let's use weekly data first, 1.79, highly significant, and the power law exponent decreases as we move from a higher to a lower resolution. So we see if we use semi-annual realized momentum variance, the point estimate is 1.51. But the interesting question is now, okay, are they statistically the same? Because that's the invariance hypothesis. So if we go back again to the highest resolution using 5 days, 5 squared daily returns, so and we estimate a 95% confidence interval using the uncertainty given by the log-log regression. We have values from 1.59 to 2.07 as confidence interval for the power law exponent, and we see, irrespective of which point estimate from the other resolutions, all of them fall into that confidence interval. And we can, the interesting thing is you can use any here. If you can also use the confidence interval for the lowest resolution, 125, you see the confidence interval is 1.17 to 1.85, and all of the other point estimates fall into that 95% confidence interval. So statistically, we can say that we would accept the invariance hypothesis. So statistically, they are the same, irrespective of which resolution we investigate here. Also, the R square is obviously very high, from 94 to 99%. Then we match in panel B, we match the exponent with the corresponding minimum value from the hill plot. What we do here also is we see how many non-zero bins are included in the log-log regression, because we cannot take the logarithm of zero entries, so we have to skip for some of the bins. We also see the critical values of the corresponding t distribution. So we see, for instance, if we operate with 7 bins, so then we have to use the t distribution with 5 degrees of freedom, giving us the critical values for the 95% confidence interval multiplied with the corresponding standard deviation of the power law exponent. So that's basically how we have to read this table. And in 3 out of 5, so in most cases here, we have to reject the hypothesis that the power law exponent is larger than 2. So that's also interesting, because what does it mean? If the exponent is less than 2, then obviously the mean does not exist. Okay, so the variance is infinite. The theoretical variance is infinite. In the next result, okay, now we want to investigate, okay, so we know now, okay, across frequencies that we have invariance, but what about if you consider each single time path? So what we do here is we do a sample split test, and we use only 3 resolutions in order to have at least a reasonable amount of data available in order to set up the sample split test. So here we use 5, 20, and 60 days as resolution. And again, we do the same thing again. We perform log-log regressions, estimate the power law exponent, estimate the confidence interval, and we see we have the same thing again. If we use the point estimates from the second sample, all of them fall into the confidence interval estimated from the first sample. So again, even within the data series, we cannot reject the invariance hypothesis. If you would run a gauge model, you would always get different estimates. But here we have statistically the same behavior across frequencies and in the time dimension. Then what we let us just go back one more time here to the previous table. Another thing that is interesting to note is here in panel B, you see in the third row the percentage of sample observations governed by a power law process. So usually what we do is usually we divide the distribution into two parts, one more thin-tailed part and one part that is governed by a power law, or the Paretian tail. The problem is, if almost 100%, if almost the whole distribution is governed by a power law, then it's not a tail anymore, right? It's basically the vast majority of drawings from the distribution. So we see here, if we have the highest resolution, 60% are governed by a power law process, whereas 99% if we use the lowest resolution. Again, if you consider time aggregation, the effect of time aggregation, it should be the other way around. But this is not what we observe in real life. Then again, what do we do here? So some people might.
Excuse me.
Yes.
May I ask what was in panel B of the first table? What was the lambda coefficient?
That is the difference between the point estimate and 2, because we want to see, is the point estimate significantly different from 2.
Thank you.
Thank you. Here we want to test. Okay, we say, okay, let us assume that the log normal distribution is that the probability that the data is generated by a log normal distribution is 50%, which is a fair coin. That is a fair coin. That is what we do first here. We assume, okay, the likelihood that the data is generated by a log normal distribution is 50%, like a fair coin. And then we say, okay, given that we have observed extreme events across frequencies, what is the probability that the log normal distribution has actually generated this data given the extreme event that we observed in the real life? So, and that's here the formula for Bayes rule, for an application of Bayes rule, and we see here in the first column of the results table that the probabilities are far below 50%. If we then say, okay, let us assume that the likelihood is 70%, that's not a fair coin anymore. There's already a strong assumption for the log normal distribution as opposed to a power law process. So let's say 70% probability that the data is generated by a log normal distribution. So how high? Then again we can ask the question, how high or what's the probability that the log normal distribution has generated the data given the extreme event that we observed in real life of this data series. And then we see even if we assume the likelihood is 70% for log normal distribution as opposed to 30% for power law, the probability that the log normal distribution has generated the data given the extreme event we have observed is still less than 50% for all of the resolutions. So we have to assume 90% probability, which is very unreasonable, for the log normal distribution, so that we have, in most cases, likelihood more than 50%. So I believe this shows that we can rule out the log normal distribution to have generated the data series. Next, what we do here is, okay, we use a different method. Log-log regressions are a traditional method used many times in many studies, also in physics. And here we use a methodology from Clauset et al. Paper, published in the SIAM review 2009, if I remember correctly. So what they do is they usually they optimize the Kolmogorov-Smirnov distance. So you might know if you consider the hill plot, it looks usually like we have the alpha hat on the y-axis, and we have here the x values, and we sort the vector of x, and then we have for each we use for each x observation as the minimum value, and then we plot the corresponding estimates for alpha hat, and then if the data is well behaving, you get something like this. And then usually in practice, what people do in practice is they use the saddle point here as the x minimum, and the corresponding value here is then the alpha hat, so the saddle point. But this is only possible if the data is well behaving, which we in real life often don't have. So the interesting thing is that this procedure from Klaus et al. It gives you, if you simulate data, then you get basically exactly this saddle point. So that's an interesting thing, which with this estimation method, and this is also, and since this, what you might have seen in the paper, that I think I have the hill plots in the appendix. The data is quite well behaving, so it looks almost like simulated data for the realized variances. So there's strong evidence for a power law going on in the data set, and the Kolmogorov-Smirnov distance based test from Klaus et al. It gives you basically the saddle point here, and that's what I apply here. And what you see here, the alpha, the power law exponent, the alpha estimates, they are for almost all frequencies below 2. And they fall, they are 4 out of 5. They fall into the confidence interval that we get from the log-log regressions. So for most of the estimates, both procedures, log-log regressions and the data-driven approach, give statistically the same estimate, or statistically indistinguishable estimates. And we see here also the same pattern, which is also interesting, which confirms the previous result, that the percentage of observations governed by power law process linearly increases as we move from a high to a low data resolution. We also see that in 3 out of 5 cases here, if we run the goodness of fit test, we cannot reject the power law null hypothesis here. This is what the goodness of fit test tells us. So whenever the test is, when the p-value is larger than 0.05, then we would not reject the null hypothesis. So again, this is again evidence for power law process. What we do here is we take a closer look on the effect of time aggregation, since this is obviously something that scholars are concerned about, because they want to have the time they want to have this effect, because if we do not have time aggregation, then all these methods, GMM and OLS and all these interesting methods that people learn, you could not use them anymore in a random environment that we have, for instance, here in this zero-cost self-financing portfolio payoffs. So here what I do here, so we plot the estimated alphas on the depending on the resolution on the x-axis. So we see a decreasing regression line. The R-square is 99.9, highly significant slope negative, and slope is significantly negative, which again which underlines either we have to say, since we have already figured out earlier, there is invariance across frequencies. So at best there is no time aggregation effect, or the effect is reversed. So it gets even worse as we aggregate time. So this is basically what the results would tell us. So the conclusions of this study, there is evidence for power law behavior in the realized variances of this momentum investment vehicle. It is shown that momentum risk is infinite. The theoretical mean doesn't exist, regardless of the resolution. this means that t-statistics for the strategy do not exist, Sharpe ratios and other correlation-based methods do not exist, and the premium is in real life not observable. So we cannot say, we cannot claim there's 1% average payoff, because with the average we do not observe in finite samples. Then the log normal distribution, we can rule out that this distribution has generated the variances, and the time aggregation effect does not hold for this investment vehicle. Yeah, this was basically in a nutshell what this study was all about, and of course now I'm very interested in your thoughts or comments on that study and the results and the procedure.